Great. So next up, we have Amir speaking about microcode updates on Chromebooks. Enjoy.
Hello and good afternoon. I'm here to talk about the in-field microcode update on Chromebooks. So is the list of people who've worked on it. So starting with, we'll be looking in general as to what the microcode update is. We'll explore what does it mean to Intel, a general format about the microcode update. Post that, we'll have a look at the problem statement that we're trying to solve here. Then a proposed solution corresponding to the problem, and a general implementation scheme and the flow updates. So starting P6 family, mid-90s, and the processors further, Intel have capability to correct the bugs or errata by loading an Intel supplied binary, and that gets loaded on the CPU. So this data block is called as the microcode update. So it has capability to patch the microcode firmware on the CPU, plus it has the capability to patch these other CPU firmwares as well. So on the screen, you'll see the general layout for the microcode update. It has a 48-byte of generic header that goes in, which has the information about the microcode version, the date the microcode version of the binary was built, and it has the information about the CPU it is being targeted for. Followed by that 48 byte of general header, you have the actual microcode update data. And the data size is also part of the header. And in some of the release, you have the extended header along with the generic header. If you want to target the microcode update specific to some of the CPU SKUs, then you need a further resolution into figuring out what CPU it's being targeted to. So that's when the extended header comes into picture. And you load, it allows you to load the microcode only for very specific SKUs of the processor that are in field. So in general, microcode update helps to ensure the stability and security of the platform once it's shipped out. So looking at the problem statement, today Chromebooks do not have a provision to update the microcode from RW region through the fit-based mechanism. So the fit-based mechanism is actually a pre-reset thing where CPU goes and looks up for the fit table, where it gets the address to the microcode data and starts loading the microcode firmware onto the microcode update onto the microcode firmware and patches the other CPU firmwares as well. So this is how your fit entries actually look like. So your fit table actually can contain multiple of these fit entries, where you have the address of the firmware you want to load, and you give the size of the update and that of the binary that needs to be loaded, and you have a generic type. So type 0 is for microcode. You have provisions to insert the other binaries as ACM, TXT. So that is being dictated by the type field here. So arriving at the problem statement here, your fit actually points to, fit is actually part of your boot block. So boot block is your RO section, and fit actually resides into it. And it points to the CPU, the microcode binary, which is part of the RO itself. So neither your fit is capable of getting updated, nor you can update the CPU microcode block, because both of them resides into the RO section. So I don't have a provision where I can update the microcode somehow, because there's no read-write section here. So this restricts my fit-based capability to load the microcode only from the RO region, which is non-updatable. So the problem lies here, where actually there is a capability for microcode to load after the reset also, but then there are restrictions on some of the firmwares that needs to be patched before the reset. So it's important that those IP firmwares gets patched before the reset is being called. So it's essential that the microcode update that goes through gets loaded before the reset. So we came up with a solution to rather pack two boot blocks now in the core boot image. So with the current implementation, what you have is your RO section contains single boot block. What we propose is to pack two boot blocks here, where each boot block are identical. The only difference between the two boot block is the fit table inside it. So the fit table in the first boot block, which I call as boot block underscore RO fit, actually has a fit table that points to your microcode binary inside the RO region. So this is same as the original implementation where nothing has changed, right? The addition to this is the second boot block that has been put in there. Now this boot block would have a fit table which would contain the address of the microcode, which would point to a microcode binary, actually pointing to your RW staging area. Now this RW staging area is capable of getting updated. So this is my RW region, and I'm capable of pushing an update here. And I would make the fit RW to point to my RW staging area. So I have now provision to actually pick up the microcode either from the original boot block, which resides in the RO region, and now I have provision to pick up the microcode from the RW region as well. So this actually needed creating one of the, we reserve one of the flash map area for RW staging area to get the read write to actually update the microcode there. Instead, the binary gets updated there. And we use the Intel top swap mechanism to actually switch between the two boot blocks. So if you want to boot from the microcode that is part of your RO region, you pick up the top boot block which is on the top. And if you want to boot with a boot block that points to your microcode in the RW staging area, you pick the other boot block which is down there. So you use the Intel top swap mechanism to actually switch between the two boot blocks. So in general, the implementation relies on picking the microcode update from the RW staging area. So this would essentially need the fit that is allocated in the second boot block to point to your RW staging area. And you somehow need a knob to switch between the two boot blocks, right? So that knob is provided by your RTC backup control register, which, like we mentioned, there's a feature called top swap, right? Where it allows you to pick either of the two boot blocks. So we'll look into general how the top swap works. So top swap is an Intel feature which is capable of inverting address lines ranging from A16 to A20. For the current implementation, what we have done is we have set the top swap enable in the descriptor. Plus, we have set the top swap. Sorry. Yeah. So if you see on the screen, it has capability to actually invert A16 to A20 lines. So for 64 KB, if I set the top swap to enable and set the top swap size to 64 KB, and you set your boot block size to 64 KB, you can actually invert the access to the boot blocks. So either at single time, when I enable the top swap, this boot block gets picked up. When I disable the top swap, the boot block which is above get picked up. So essentially both the boot block are now pointing to different fits. And when I boot from the boot block which is on the first one, I'm able to point to the microcode binary in the RO region. If I pick the boot block which is below, I'm able to patch the microcode from the RW region. So this allows me to actually update the microcode region and use the microcode update from there. So this backup control register is part of your RTC register block, and you can just write 10 to it as a switch to enable the top swap and disable the top swap. So we'll look at the general flow as to how the top swap or the microcode update would work with the architecture that is being planned. So let's suppose you are into a kernel and you booted with your active firmware block RWA, and you have rolled out an update which is having the microcode update. And since your active firmware block is a RWA, the firmware gets loaded into RWB. Now the firmware patch that is the update that has comes with an updated microcode binary as well. So the microcode version in RWA, which is your current booting slot, was version V2, and the microcode version in the staging area, which the other boot block points to, is also V1. And the microcode version that has come as a part of update is version V2. And your top swap is set to 1 because your normal boot would always have your top swap set to 1. So you'll essentially boot with the boot block having fit pointing to your RW region. So when you reboot the system, your boot block that gets picked up, your fit that is currently pointing to your microcode staging area, which holds the version V1. So if you look here, the staging area still has the version V1, and your fit points to it. So as soon as you trigger a reboot, your version V1 gets loaded. You come to boot block. Vboot sees that the RWB has been updated, and the firmware next is set to firmware B. So it starts picking up the firmware B. Now boots further, picking up the firmware B, and comes to RAM stage. So the RAM stage has a driver which sees a difference in the microcode version between the slot and the microcode which is stored in the staging area. So as we mentioned, the microcode in the update would be version V2, and the one you're running into is V1. So there's a difference in the version there. So what it does is it updates the staging area with version V2, and your fit now was pointing to staging area, right? So now your fit actually points to your version V2 here. So you disable the top swap while doing it, just for a precautionary way. If the update is broken, you still have a way to point your microcode to your RU region, and then you issue a reset here. So once you issue a reset here, your alternative fit now would point to your version V2, which just got updated in the staging area. So just before the reset, you actually started picking up the version V2. So earlier you actually booted with version V1. Now you have version V2 running on the CPU. Now you come to the same check where you see the slot RW is updated to V2, the staging area is V2, and the current running version is V2. So you just do a flash write protect for the staging area, and you boot further. So this is the update flow you would see with the plan implementation. Now coming to the recovery part, where due to some reason there is failure, right? So your microcode that gets loaded after the update is version V1. You come to vboot. So the cases for recovery would be your staging area after the update gets updated with version V2. Your microcode version in the RO cannot get updated. So still it holds the reference to version V1. And the recovery case, the default boot scenario is with top swap enabled. So issue a reset either by manual recovery or developer-based recovery, right? You issue a reboot. The microcode version that gets loaded after the update was V2. You come to the boot block. So if recovery is set and top swap bit is set to enable, what the logic would do, it would set the top swap to 0. So essentially, it will make the fit to point to your RO region. So it'll pick up the alternate boot block that we have that was part of the original implementation. So now after this, you issue a reboot. Now your boot block gets picked up is the upper one, which has the fit, which points to your RO microcode update. So on the reset, the RO microcode update gets picked up and you boot further through the recovery. So this is in general the recovery case. So this is the first boot case where your actually staging area is empty. Your microcode binary in your RO, RWA, RWB is all same. So all are set to version V1 because this is basically when you build an image and flash it, or a factory flash where you flash the image. So all the RO, RWA, RWB would have the same microcode binaries. And the initial top swap state is the bug control default, which is set to 0. So start booting, and then the same RAM stage driver sees that the staging area is empty. It copies the microcode binary V1 into the staging area, issues a reboot by setting the top swap to enable. So this would be your normal case where top swap would always be enabled for the normal case, and for recovery case, you'll have top swap always disabled. So it starts picking the version V1 from the staging area, boots further, gets into RAM stage, applies the flash protection to the microcode staging area, and boots further. So this is pretty much the implementation flow with the microcode updates. Yeah, any questions?
So my first question is just for understanding, does this microcode update, it doesn't persist on the CPU, right? So it has to be reloaded on every boot, or how
Yes.
does that work? Okay. So does that mean once you have an update, every normal boot after that, that's not recovery, will load the updated boot block in RW?
Yeah, so the scope is only lasting till the reboot. So for every reboot, you'll have to apply the microcode again.
Okay, and then when you want to boot in recovery, then you first boot into the updated boot block, and that one will reset the top swap to 0?
Yes.
But what if it's broken and doesn't do that?
So then there's an option for normal, like forced recovery, where you see that the system gets hanged or it gets bricked, right? So you have a battery cutoff option through the buttons, right? So if you press that, you have battery cutoff and your RTC BAT register, right? It goes to 0 by default. So that's like absolute recovery.
Okay, but the user has to manually do that,
Yes.
right? There's no automatic way to recover from that?
No.
Okay.
So this is like case where the system is bricked and you can't like do anything.
Sure. I mean, so on a normal Chromebook, it's not possible to put it in a state where it won't automatically recover, right? Because it always reads from the read-only in that case.
So the binary that gets updated, right, has already been validated at the Intel end and the Google end. So whatever has been pushed as a part of the update is the same binary. And the same gets updated in the staging area too.
But oh, so is the area flash protected where that boot block is in?
Yes,
like,
and
okay.
the one you mentioned would all in the recovery scenario, right? Your CPU binary is also already like the microcode binary is already part of your RO, so that can never be tampered. So you'll also always have a same copy of microcode there.
Right, but you need to manually trigger it to boot that.
Yeah.
Okay. And one more thing. Isn't this a way that the RW firmware can use to circumvent the RW firmware rollback protection? If it so it can essentially attack the read-only TPM firmware space with that, right? Because it can reboot into a boot block that is controlled by the RW firmware, and then it can use the control over the TPM to drop or modify the TPM spaces that it wasn't supposed to have access to.
So basically, this would apply way before the reset is done, right? So
I mean, so the fundamental problem here is you're running your boot block out of read writable space, right?
No, RO.
Okay. But then how do you update it?
Sure.
It's just
So if you look at the files, right, it's been, so those blocks, right, the one in the top is all RO.
Right, but I mean,
That was the
other one.
problem statement.
Yeah, so there's a few pieces to this to note. One is that last bullet point where it says some IP firmware can be patched only during reset. That actually should be also discussed about what type of resets. There's different, there's warm and cold, and some of that only gets applied during warm versus cold. And to your point about the attack vector, it is, in this particular case, the two boot blocks are sitting in RO, but one of them has a fit entry to a region that's in RW, which is only containing the microcode update.
So
And
all the code is in RO still.
yes, the code is still in RO. And then go to the next slide.
Sure, if
One
you-
of these guys. Yeah, so that's the RO versus RW layout, where the green is RO, and then the blue and the black down below is RW.
Okay, thanks. So that's awesome.
Yeah, so there is, I mean, to your point, like you're essentially on, there's a, will you, I mean, to go to the next one, I think we had a sequence in time.
Okay.
Yeah, so like it's these guys between the resets where that's like your duration of a mismatch of RO and an RW in the hopes that it works more than anything. But that is your attack vector. If you can load a microcode, which is signed and encrypted by Intel, and then you could take over the actual execution of the CPU to make it do something different. But that's the risk, is essentially what that opens up.
Okay, thanks.
Can you load the old microcode, which is? Can you load old microcode, or is it going by version number?
You can load the old microcode too.
So then you can basically attack this by.
Yeah. So the other bit was go to, you had FPR somewhere, which wasn't mentioned in here, but it is in there.
Yeah, it's there in the last one. So
Last
you have
one?
it.
Yeah. So that is, what does it stand for? Flash protection
Flash-
region. So basically, in the SPY controller, you could. So I mean, ignoring a physical attack,
But then,
the flash protection register will protect access to that specific region.
Understand, but if somebody puts if you update microcode and you manage to update it to an old version, which is flawed for whatever reason, the old version will be executed from RW if that address redirection is enabled.
I mean, that's what Aaron mentioned. You are actually doing a flash protect on that. So while booting through the kernel, you would not have actually a right access to that.
But at some point you had right access to that to update the microcode, right? So what when you're updating the microcode, you put there not the newer but older version?
Yeah,
If
that
there
could
is an
totally
attack.
happen for sure. But that's it's also within the purview of our boot flow of already choosing things to verified boot, right? That's all packaged together, and we're just taking it from one area and putting it into another.
This is part of the chain of trust. It is not every link in the chain of trust. So something else would be preferred to verify that you're actually about to load the right microcode. That's like in UE5 with something like capsule update, for instance.
So one thing we
There's a-
planned was to have a smoke test before loading it. So it's like the staging area, right? You actually you do a test where you actually load the microcode from the staging area. If the microcode version turns out to be invalid, you actually drop that and just reboot, setting the top swap to 0.
Right. That's why what I'm saying is that this is the process, and to prevent things like rolling back to an older microcode, there has to be some other thing in the process of like delivering to the system. So yeah.
Thanks for the presentation. I have a question. Can this method be applied to other binary blobs like ME image?
So yeah, that's work in progress.
That's a work in progress. Okay.
Yeah, I think it's definitely a work in progress. The unique thing here, I mean, I'd say, and I think Amir would agree with me, this is a solution with the pieces that we have to work with. It is not an ideal solution, but this is what's baked into existing hardware and some of the assumptions in the Intel's designs. And then, yes,
Could you elaborate on what's the hardware limitation that you
well, so, sorry, this is also, it intersects with Chrome OS's designs and intent, which is we care about not bricking a machine. Yes, and we were talking earlier how it opens up a potential vector, potentially of bricking a machine, but fundamentally we don't want to ever brick a machine. And recovery in that particular case is a first-class citizen in that you can always at least get some input or like maybe output from a device that you can get it back into a clean state. So that's why we have an RO, which actually contains all the pieces to basically re-image everything on your machine. And then if you don't care about that, and there's various, many designs actually go down that path, where it's like you're basically in a crippled state. You don't actually know, you just know the thing's broken. Sometimes maybe there's a sideband path for updating, sometimes there isn't. Or for that, it could be a USB type thing, an assisted USB through the ME or something like that. That's also a possibility. However, you don't really have a lot of input to the end user that things are in that state. What are you supposed to do? I hit the button. It just looks like it's dead. In Chrome OS for Chromebooks and things like that, our whole goal is to always provide a signal to the user what is going on. In that particular case, that's why we fall back to a full RO path. And we can display instructions and that sort of stuff so that you can get the system back into a normal place. So the moment you say, I don't care about that, you don't need a lot of redundancy, you don't need, that's what this is trying to ensure, to allow the RO path as well as, updating all these other pieces. And if you don't care about risking that presumably brick, then you can definitely just throw out a lot of these things.
server, you do care, but not to that extent.
Yeah, if you have a sideband way to recover your system, then yes, right? Which is if you have a BMC connected to a control network, that's a pretty easy way to get stuff pre-provisioned.
Okay, I have a question. Actually, two. Is a top swapper reliable? Because in my past experience, we found top swapper can be like a mistaken set up because the power sequencing. If power sequencing was not good, then top swap can be like mistaken set. Then the chipset just put another boot block. So I wonder if top swap is reliable.
For the newer platform, we find it like we have not
It's
run
hardware.
into instances where it's not reliable. So every time we have tested this,
Mhm.
we were actually able to switch between the fit table and actually able to switch between the microcode binary in the staging area and the one sitting in the RO. So pretty reliable. I'm not sure what your experience is.
Yes,
With,
it's because we have board management controller on the board to control the power sequence. And then we found if some kind of condition that make PCH not happy, so PCH will mistakenly set out the bit,
so this is for which platform?
Haswell.
Okay, sure.
Yeah, at that time, I believe the fit table is already there. So,
Yeah.
and then the second question is, can you roll back to the previous slides for the flow? And then, yeah, this
Just
one.
let me know.
Yeah, no, next one.
Next one.
Yeah, I see you have fit table loaded. So yeah, but you have two boot block. Then I wonder if you need to have two fit table in the design.
No, actually, we wanted to have a root of trust. So, is your question like we could have packed the
No,
two
I mean,
fit
my
table
question
in
is, fit table contains the information from microcode, the absolute location.
these?
Yeah, so if you put you have two boot block to contain two different version microcode, but you only have one fit table, so that means if fit table the microcode size does not match, or like their new one is larger than the previous one, or smaller than previous one, then the fit table definitely needs some change, or you have multiple microcode.
So we actually populate the fit table on the runtime, where it picks the microcode binary and fills in that data as to where the microcode binary is sitting in, and the size of the microcode binary and the every entry that goes into the fit table, right? So that's done by the code. So pretty reliable.
So Amir, I think you have a picture of this where you listed the two boot blocks. There's actually two different fit tables.
Two different fit
Yeah.
table.
Yeah.
Yeah,
So-
but is
Yeah, this is the picture.
But I think
250.
he gets the point, right?
My question. Yeah, this one is my question.
Okay.
Okay, thank you.
So both the boot blocks would be part of your RO. So any other questions?
More questions?
All right. In case if you have further questions, do drop the mail. We'll respond to the queries here. So, all right. Thank you.
Thanks again.